the antiderivative, or something that we call the indefinite integral. And we've already kind of looked at the fact that the area underneath the curve, it has something to do with the antiderivative function. Okay? Or another example would be the area under the derivative curve of the displacement, which is velocity. So area under velocity is related to the displacement on the position function. Okay? So there's some sort of relationship there between area under the derivative and the antiderivative. So we really just want to today just undifferentiate things. We want to find the antiderivative. And we'll look further at kind of this application of it later, but we just want to undifferentiate things. So if we can differentiate things, we can undifferentiate it. It's kind of like if we can add something, we can subtract. There's an opposite. There's an algebraic opposite. If we can times something, we can find the opposite divide. If we can square something, we can find the opposite square root. So we want to undo a derivative. Okay? We want to do essentially the inverse of it. So if I start with x squared as my derivative function, okay, so small f is my derivative, what is the big F, the antiderivative function? Okay, well, the antiderivative, if I end up with x squared, well, I must have started with x cubed. But the problem is if I multiply, do my power rule, I get 3x squared. Well, I don't have 3x squared there, so I can just accommodate that by dividing by 3. Now, one other piece here that we have to be considerate of is this big F could have been x cubed over 3, and it would have given us x squared, but it could have been x cubed plus over 3 plus 3, or x cubed over 3 plus 18, or plus negative 59. We don't know because this differentiates to 0, so this disappears. So we have to make sure we account for that. And we're going to account for that with a plus c. Okay, so it's really important because this is what we call an indefinite integral. We need to use a plus c because we don't know exactly the vertical positioning of that function. Okay? So in what we use it for area, it doesn't really matter either because we just want to find displacement. So, but for the indefinite integral, we need the plus c. Okay, for this one here, there's my derivative. So my antiderivative must have been a power 4. I need to divide by 4 because if I don't have a divide by a 4x cubed here, I just have an x cubed. So I need to get rid of that times 4 when I bring the power down. And again, we're going to plus c. And then we can generalize this. If that's the power 5, we start with a power 6. We need to account for the extra times 6. And then we also need to account for the plus c. So if I want to anti-differentiate, so if f prime is equal to fx, then this little symbol here means the antiderivative, or the integral. And it's actually a little stylized s, which actually means sum, because if we take a look at the notation, this is actually the area. We're actually summing up area. But that actually means s, or sigma. So really that somehow evolved into that integral notation. Okay, so if we want to take the antiderivative though, we would just look at it as big F plus c. Okay, so we want big F plus c. That big F is going to have a power rule to it. So if we have the antiderivative of x to the power n, we're going to increase the power by 1 and then divide by that to account for that, the coefficient when we differentiate, and we need to always have that plus c. Now this could be written as what we call a differential equation, showing that if the derivative equals x to the n, what's implied is we solve this differential equation for y, which means we anti-differentiate this expression. So again, we get the same thing. Okay, so we see it written like this. Sometimes we see it written like this, and this is called a differential equation, where it's implied we solve for